Hello everyone, this is Professor Roman. Let's continue the field theory lectures. Before getting into a detailed discussion of the modern Galois theory, I want to take a quick look at a general concept that occurs in mathematics, that of closure, because we will need it for the Galois correspondence. As shown in this figure, you might be familiar with the idea of the closure of a non-empty subset of the plane. If S is a non-empty subset of the plane, by definition, its closure is the set consisting of S together with all of its limit points, also known as accumulation points. So this is a very simple illustration. In this case, the set S could be a lot more complicated than this. It doesn't have to be connected and so on. When S has the property that it's equal to its own closure, in other words, S contains all of its limit points, then we say that S is a closed subset of the plane. This operation of sending a subset of the plane to its closure is a special type of closure operation. Closure operations appear in many branches of mathematics: analysis, topology, algebra, logic, and others. The closure operation of subsets in a plane is a form of topological closure because it involves limit points. Our interest, however, in closures is of the algebraic type. And here is the general definition of a closure operation, or closure operator. Let P be a partially ordered set. A map CL of P to itself is a closure operator if the following three properties hold. It must be extensive, which means that P is less than or equal to its closure. Idempotent, if we apply the closure operator twice, it's the same as just applying it once. And order preserving, if P is less than or equal to Q, then the closure of P is less than or equal to the closure of Q. So the element CL of P, the closure of P, this is called the closure of P, and an element is said to be closed if it's equal to its own closure. I'm going to denote the set of all closed elements of P by capital CL of P. Now, it's clear that from the idempotence property of a closure operator that the closure of an element is closed. That's rather important. It's something you would expect. Also, if Q is closed in P, then Q is equal to its closure. So the closure of a closed element is the element itself. If the element's closed, taking its closure does nothing. The image, then, of a closure operator is the set of closed elements. And this map is surjective. That's what we just established. You might recall when we first began our study of field theory, we talked about the family of subfields of a field, and we said that that family formed an intersection structure. Again, that's covered in Appendix A, the notion of intersection structure. It's a very simple idea, but really quite important, especially in its relationship to lattices. Here's another example of an intersection structure. So if I is an intersection structure on a set X, that means that I is a family of subsets of X, and that family is closed under intersection. And if we have a closure operator on that family, then the subfamily CL of I of closed sets is also an intersection structure. In other words, the intersection of closed elements is again closed. And here is the proof. Let S be a subset of the closure of I. Or this, I shouldn't have said that. The family of closed sets of I. If S is empty, the intersection of the empty family is the whole parent set X. And X is closed because its closure contains X, but there's nothing bigger than X, so X is closed. If S is not empty, and it looks like this, then the intersection of everything in S is contained in each one of the elements, say S sub j. And so by one of the properties of closure operators, the closure of the intersection is contained in the closure of Sj, but each element is closed, so that's just Sj. Sj was an arbitrary element of capital S, and so the closure of the intersection is contained in the intersection of all of the elements, which by the extensive property is contained in the closure of the intersection. So these are equal, and that means the intersection is closed. So the family of closed elements of I is an intersection structure. Well, we can now examine the Galois correspondence of a field extension. And for this, we will require some notions. First, we have fixed fields. If F is a field, and sigma is an automorphism of F, and S is a subset of the field F, then sigma can act on S in two different interesting ways. It can send the set S into itself. Sigma of S is contained in S. When that happens, we say S is sigma invariant. So sigma maps every element of the set S to an element of the set S. It doesn't have to be the same element. It just has to stay within the set S. But we will also need the stronger property that sigma sends every element of S to itself. And so for that, we need a definition. Let F be a field and let sigma be an automorphism of F. An element alpha in F is fixed by sigma if sigma sends alpha to itself. Otherwise, we say that sigma moves alpha. If sigma fixes every element of a subset of F, we will say that sigma fixes S, or, for added emphasis, to distinguish between sigma invariants, I will try to say sigma fixes S element-wise or point-wise. But it's not, strictly speaking, necessary to say sigma fixes S means sigma sends every element of S to itself. The fixed field of a subset I of the group of automorphisms of F, denoted by fix I, is the set of all elements of F that are fixed by every automorphism in I. So here's what it looks like in symbols. It's a set of all alpha in F such that sigma alpha equals alpha for all sigma in I. And I'm going to leave it for you to prove that fixed fields are indeed fields, subfields of the field F in this case. So if F is a field, I is a set of automorphisms of F, fix I is a subfield of F. The other important element of a Galois correspondence are the Galois groups. The Galois group of a field extension FE, denoted by GFE, and there are other notations, some authors will write GAL sub F of E, is simply this group of automorphisms of E over F. So we're just changing the notation and the name, and we have this by definition. And we'll also say that GFE is the Galois group of E over F, as well as the Galois group of the extension FE. The Galois group of a polynomial, P of x over F, with respect to an algebraic closure, F bar of F, is the Galois group of the unique splitting field of the polynomial in F bar. And I'm going to leave this for you to prove also that if we have a tower FKE, then the Galois group of E over K is a subgroup of the Galois group of E over F. Notice that K is bigger than F, but GKE is smaller than GFE. So I may refer to GKE then as a Galois subgroup of GFE. Now with this introduction of Galois groups, we can restate some earlier facts that we learned. I'll go over these briefly, but I would strongly urge you to think about each one of these, make sure it makes sense to you. If FE is algebraic, then the Galois group of E over F is the same as the set of embeddings of E into itself over F. FE is normal if and only if, this is the definition really, the set of embeddings of E into E bar over F is the Galois group. FE is finite implies that the size of the Galois group is less than or equal to the separable degree of E over F, which divides the degree. All this is old news. It's just couched in the language of Galois groups. FE is finite normal implies that in fact the size of the Galois group is equal to the separable degree, which again divides the full degree. The finite Galois, if FE is finite Galois, implies the size of the Galois group is equal to the separable degree, which is equal to the degree of E over F. Let's look at a couple of examples of Galois groups. These are relatively simple ones, but it'll give you a sense of what's going on here. Look at this polynomial, rational polynomial, x squared minus 2 times x squared minus 3. The root set, the complex root set of this polynomial contains these four real numbers: square root of 2, negative, square root of 2, square root of 3, negative, square root of 3. The splitting field for P of x in C is Q with these two roots adjoined, which will then catch the other two roots as well. To find the Galois group of P of x, or in other words of this extension, we know that any sigma in the Galois group of S has to map roots of this minimal polynomial square root of 2 over q, which is x squared minus 2, to roots of this polynomial. And similarly, sigma has to map the roots of this polynomial, which is the minimal polynomial for square root of 3 over q, to roots of the same polynomial. So square root of 2 has to go either to itself or to negative square root of 2. Square root of 3 has to go either to itself or negative square root of 3. Now, because this is a finite Galois extension, where to go there, the splitting field extension, we know that the size of the Galois group is the degree of the extension, which is 4, which means all of the maps I just discussed, square root of 2 going to itself or to negative square root of 2 and so on, are in fact, or lead to in fact, members of the Galois group. These are just permutations within this set. So besides the identity map, we have these three maps. Square root of 2 goes to itself, square root of 3 goes to negative square root of 3, square root of 2 goes to negative square root of 2, square root of 3 is fixed, and in this case they're both moved. And I'll leave it to you to show that this is the Klein-4 group. It's abelian, order 4, that only leaves two choices. And incidentally, this example shows that while every member of the Galois group of a polynomial is a permutation of the roots of the polynomial, not every permutation of the roots comes from a member of the Galois group. So put more simply, the Galois group of a polynomial is often a proper subgroup of the symmetric group on the roots. As it is in this case, there are 4 roots. The symmetric group would be S4 of order 24, but we only have 4 members in the Galois group. Another example, P of x is x to the 4th minus 2. This has a complex root set here. Splitting field extension, we adjoin to Q 4th root of 2 and 4th root of 2i, or just I, and that will catch everything, catch all 4 roots. We can decompose that into a tower to help us get the degree. The lower step has degree 2, it's normal. The minimal polynomial of 4th root of 2 over q with I adjoined is x to the 4th minus 2. So the upper step has degree 4. So the degree of the splitting field extension is 8. Again, this is a finite Galois extension, which means the Galois group also has size 8. And here are the 8 elements of the Galois group. In this case, it's easy to see this is non-abelian. It contains 5 elements of order 2 and 2 elements of order 4. And the only non-abelian group of order 8 with these specific requirements or element orders is the dihedral group, D8, the symmetries of the square. And I'll let you do the group theory necessary to verify that and find, if you wish, a suitable pair of generators, what are usually known as the reflection and the rotation. All right, so we now have fixed fields and we have Galois groups, or Galois subgroups of the main Galois group. Now we can look at the correspondence. And to put it in context, one of the most important theorems in linear algebra, group theory, and ring theory, and we studied all of these in previous courses, is the correspondence theorem. Here it is for groups. G is a group, N is a normal subgroup. We have here a couple of intermediate subgroups between G and N. The canonical projection map, I didn't put that on here, I guess I should have. Anyway, projects G onto G mod N, the quotient group, and it projects all of the intermediate subgroups onto their quotients, mod N. According to the correspondence theorem for groups, this map is an index-preserving lattice isomorphism. A lattice isomorphism is the same thing as an order isomorphism. It's a bijection that preserves order in both directions. It and its inverse must preserve order, and that's important. Order isomorphisms also preserve meets and joins, and so they are lattice isomorphisms. So this is an index-preserving lattice isomorphism between the subgroups of G containing N and the quotient groups of G mod N, the subgroups of G mod N. The cornerstone of Galois theory is another type of correspondence called the Galois Correspondence. But in this case, it is an index-preserving lattice anti-isomorphism, so it reverses order in both directions. It's an order-reversing isomorphism between the intermediate fields of the extension Fe and the subgroups of the Galois group. In fact, we'll see, and the Galois subgroups of the Galois group. So unlike the correspondence theorem for vector spaces, groups, and rings, which are correspondences between the same type of algebraic structure, the Galois correspondence is a correspondence between fields and groups. That has some unique advantages, which we'll discuss. But I do want to mention one other thing, just for context. The Galois correspondence is actually a special case of something called a Galois connection, and I didn't discuss that in the book. The Galois connection works between two partially ordered sets. I don't know, maybe I should add a topics chapter on the Galois connections. If I can remember to do it, I will. If not, certainly something you can look up on the internet. So the Galois correspondence provides a means for translating certain problems in field theory to problems in group theory, some of which seem to be more tractable, more easily solved than their field theory counterparts. And that is why the Galois correspondence is so important. So after we describe the correspondence in detail and study its basic properties, we will study its most celebrated consequence, the connection between field theory and group theory, which is the following. A polynomial p of x with splitting field s in f bar. So we have a splitting field extension f to s. That would go on the left side of the Galois correspondence f and its splitting field for p of x. This splitting field extension is solvable by radicals. In other words, S is contained in a radical tower if and only if the Galois group of S is solvable. It is solvability by radicals, what we're really interested in, what we're after, because it is essentially expressible by formula. We will, in due course, define and discuss the basic properties of solvable groups. So if you're not familiar with them now, not to worry. As I think I mentioned, certain groups, such as the symmetric groups Sn for n bigger than or equal to 4, are known to be unsolvable, can prove that they are not solvable. And so polynomials whose Galois groups are these symmetric groups are not solvable by radicals. To describe the Galois correspondence of an extension, Fe, let script f denote the family of all intermediate fields. So again, from the picture, script f, all the intermediate fields between f and e, and let script g denote the family of all subgroups of the Galois group, all subgroups. Both of these families are intersection structures, and so they're complete lattices under set inclusion. Here is a picture. The intermediate fields are over here, the family script f. The subgroups of the Galois group are over here, script g. Now, the Galois correspondence consists of two maps, one going from the fields to the groups, from script f to script g, and one going in the other direction. The Galois group map, which I'm going to denote by Blackboard G, fortunately I have another font available, sends script f to script g, intermediate fields to subgroups, and it sends an intermediate field k to the Galois group GKE. So this is all the automorphisms of E that fix K. The fixed field map goes in the other direction, this way, and it takes a subgroup of the Galois group and sends it to its fixed field. So F, Blackboard f of I, is the set of all field elements that are fixed by the automorphisms in I. This pair of maps is called the Galois correspondence for the extension Fe. And I'm going to use the following terminology, not necessarily standard, some of it may be. The maps F and G are Galois maps. The intermediate fields and the subgroups together I'm going to call the elements of the correspondence, because sometimes I want to refer to both families at the same time. I can do that by calling them the elements of the correspondence. The images of F are the fixed field map are obviously the fixed fields, or I may call them fixed subfields because they are subfields of E. Might be better to call them fixed intermediate fields, but usually they're just called fixed fields. The images of G are on this side, and I will call them the Galois subgroups of the correspondence. Now, first property of the Galois maps, the Galois correspondence, the Galois maps are order reversing. So, I'm sorry, I have a little allergy problem, so please forgive my throat clearing. On one side, K subfield of L implies Galois group of E over L is contained in the Galois group of E over K. So I've reversed the order here. K is smaller than L, but the Galois group of E over K is bigger. Okay. And here it is for the fixed field map. Again, reversing the order. Well, there's not much to this, actually, as you can see from the proof. Any automorphism in GLE fixes L pointwise, so it obviously fixes K pointwise. So anything in here is in here. And similarly, anything fixed by J, any field element fixed by J, is obviously fixed by I. And so we have this relationship. So that's easy. By far the easiest part of discovering the properties of the Galois correspondence. The next item is what I'm going to call the round-trip maps. And that is the composition, FG. So this starts with an intermediate field. You go to the Galois group, then you go back to the fixed field. So this is what it looks like. K is your intermediate field. You take the Galois group, then you take the fixed field of that Galois group. And for GF, you take a subgroup of the Galois group, you take its fixed field, and then you take the Galois group of that fixed field. These are the round-trip maps. To put these descriptions more directly, FG sends K to the subfield of elements of E that are fixed by every automorphism of E that fixes K. That's a mouthful of words, but I think it's fairly important that you spend enough time with this so that doesn't sound just like gobbledygook. Okay, see what can happen if we come back to the picture here. Here's K. We're going to go across, down here. Well, actually, okay. Here's the picture I want. We go from K to its Galois group, and then to the fixed field of the Galois group. So these are the things that are fixed by everything here. In other words, by all the automorphisms of E that fix K. But it's possible that the automorphisms of E that fix K fix some other elements as well as those in K. May fix more elements. So this item contains K, but the containment could be proper. And we'll discuss that at length. We've got the same deal over here. GF sends I to the family of all automorphisms that fix the elements of E that are fixed by I. It may be possible that the elements of E that are fixed by the automorphisms in I are also fixed by other automorphisms in this Galois group. So this could be strictly larger than I. Now the importance of the round-trip maps comes from the fact that they are closure operators. So we have a theorem. We have a Galois correspondence for the extension FE. And as shown in that figure I just showed you, the round-trip maps are closure operators. So let's take a peek again at that figure. For G followed by F, we come across here to the Galois group. We go back to fixed field. This is, in fact, the closure of K. That is to say, we'll know that once we've proven that the round-trip maps are closure operators. This round-trip map, first G then F, once we've shown that's a closure operator, we will know that the GF of I, so that's this Galois group, is in fact the closure of I. So the closure of K is FG of K, and that's the fixed field of the Galois group of E over K. You know, it's tempting when you see G of K to read this as the Galois group of K. It's not. It's the Galois group of the top field E over K. K is what's being fixed point-wise. Similarly, the closure of a subgroup of the Galois group, I here, is GF of I, so that's first you take the fixed field of I, then you take the Galois group of E over that fixed field. The image of each Galois map is the set of closed elements in its codomain. So if we restrict the Galois group map, the codomain of the Galois group map, to the closed subgroups of the Galois group, we get a surjective map, and similarly, if we restrict to the fixed fields here, we get a surjective map. So another way to put this is to say that the closed subgroups of the Galois group are precisely the Galois subgroups, GKE. And the closed intermediate fields are precisely the fixed subfields, or the fixed intermediate fields between E and F. As for proof, the extensive property for FG is this property. K is contained in, or less than or equal to, contained in subfield of FGK, which is the fixed field of GKE. This has to hold for all intermediate fields K. Well, this just says that the elements of K are fixed by the automorphisms V that fix K. It's almost a triviality. Well, I guess it is a triviality. Same thing here. This says that every automorphism in I fixes all of the elements of E that are fixed by every element of I. So again, it's going to take a while to get comfortable with this correspondence. It's more complicated than the correspondences you see in linear algebra, group theory, and ring theory, because you got two different types of structures. And so it takes a while to get comfortable with it, and the wording can seem confusing. And so it's patience is required here. There's no question about it. And review is required. Okay? So when you look at these things, when you look at this is the automorphisms of E that fix I. The automorphisms of E that fix the elements that are fixed by I. Okay? An automorphism in I is also an automorphism of E that fixes the things that I fixes. I don't know if that's helpful or not, but it's another way to phrase this. The order preserving property of the two round-trip maps holds because each Galois map is order reversing. So if you apply two of them, you preserve order. So we have the extensive property, and we have the order preserving property. We have to check idempotence. Okay. The extensive property, extensiveness of Fg tells us this. You apply Fg to K, it may get bigger. If we apply the order reversing map G, we have this, but GF here is also extensive, so GF of GK is bigger than or equal to GK. We have GK on both ends, so we have equality. If we take K and we apply G, and then we apply F, and then G again, we wasted our time. All we had to do was apply G. If we apply F to both sides of this, we have the idempotence property for Fg. Fg is the same as just Fg. And the idempotence property of GF is proved similarly. There's a nice symmetry here that you can take advantage of. So it wouldn't be a bad idea to take a clean piece of paper, put this away, and try to prove that GF is also extensive. For part 2, which is that the images of the Galois maps are the closed elements, first of all, this equation shows that GK is closed because it's equal to its closure. To get the closure, you apply GF. So the closure of GK is GK. So GK at least is closed. The image of, under Blackboard G, the image of the Galois map contains only closed elements. But there's one more thing we have to show, and that is if I is a closed subgroup of the Galois group, then I is equal to its own closure, which is by definition GF of I, which is in the image of G. So not only does the image consist only of closed elements, but every closed element is in the image. And so the image of G is precisely the family of closed elements. And I'll let you prove the dual here. The image of F is the closed elements here. Okay. Well, what's next? What we have just proven is that if we restrict the codomains of the Galois maps, we get surjective maps. That's nice. But if we restrict the domains also to the closed elements, then we get maps that are order reversing inverse bijections. That is to say, order anti-isomorphisms, and that's even better. So, definition, and this is not standard, but I think quite reasonable. We have a Galois correspondence. We refer to the maps G and F, the Galois maps, that are both domain and codomain restricted to the closed elements, simply as the restricted Galois maps. So the restricted Galois group map and the restricted fixed field map. These maps are now inverses of one another, because if K is a closed intermediate field, so K is equal to its own closure, that simply means that K is the closure of itself, and this is the definition of closure, and so FG sends K to itself. It's the identity, the composition F composed with G. And similarly, the composition G composed with F sends I to itself, so that's the identity. Composition in both directions is the identity. We have inverse maps. So both restricted Galois maps are order reversing bijections, and so they are order anti-isomorphisms. And that's the statement of this theorem. Specifically then, we have K contained in L if and only if GLE is contained in GKE. This goes in both directions now, and so does this one. Well, we know that the families of all intermediate fields and all subgroups of the Galois group are intersection structures, and therefore complete lattices. And an earlier theorem, 5.2, then tells us that the families of closed elements on both sides also are intersection structures, and therefore complete lattices. Remember, we proved the intersection of closed elements is closed. That was part of that was very early in our discussion. We were talking about closure operators. But there is a word of caution here. The meets are intersections, but the join is more complicated. And the join in this lattice of closed elements, closed intermediate fields, is not the same as the join in the larger lattice F. We have a similar problem with meets, but I'll just discuss joins here. And also that applies to the group side also. You see, in this lattice of closed intermediate fields, the join is, by definition, the join of a subfamily S is the smallest closed intermediate field that contains S. It's the smallest element of this lattice. Whereas in the lattice F, the join of S is the smallest intermediate field, period. It's the smallest member of script F. So it could be closed or not, doesn't matter, it's not relevant. The smallest intermediate field that contains S. So our job descriptions are different, and that's not surprising. We're in two different lattices, there's no reason that the joins should be the same. Even though one is a sublattice of the other, it doesn't matter. They're different lattices. Okay. Because the restricted Galois maps are order anti-isomorphisms, they're also lattice anti-isomorphisms. That's true in general. It's got nothing to do with Galois correspondence. Order isomorphisms are lattice isomorphisms, and the same for anti. And so that is expressed here, that the Galois group of the intersection is the join of the Galois groups, and this is the anti part. We go from meet to join. Okay. If they were order preserving, you would go from meet to meet, and join. The Galois group of the join is the intersection or the meet of the Galois groups. This is what it looks like for two Galois groups. Same deal for fixed fields. And I'll let you kind of read that carefully. We can now summarize. And actually the summary looks a lot better than what we've just been through. We have a Galois correspondence for an extension Fe. The maps G and F are order reversing. The codomain restricted maps are surjective. The round trip maps are closure operators. And finally, the families of closed elements are intersection structures. Intersection of closed elements are closed, and so they are complete lattices, meet and join. Moreover, the restricted Galois maps, and by restricted I mean both domain and codomain are restricted to the closed elements. These are inverse lattice anti-isomorphisms. It's the nicest property you could have for order reversing maps. Lattice isomorphisms that reverse order, so lattice anti-isomorphisms. Okay, we're going to move on in the next lecture to one more property of the Galois correspondence, and I would strongly urge that you go through this lecture again if necessary before moving on to try to cement some of this in your mind. This summary, it's really important that you carry this with you without having to look it up.